Right, so welcome to Lean Together 2025. Our next speaker is Lorenzo Luccioli, who will tell us about information theory in Lean, the data processing inequality.
Thank you very much. So yes, I'm going to talk about a bit about information theory, and the things I will talk about have been. Oh, sorry. Yes, this works. So the things I'm going to talk about have been developed during the testing lower bounds project, which is led by Rémy Degenne and done mainly by Rémy and myself. And some of the things I'm going to talk about are also going to be already in Lean before the project, actually. And so what information theory is, so it is a branch of mathematics that tries to understand what information is and how do we quantify information. And a concept that's closely related to information is that of information divergences. So imagine you have two probability distributions, mu and nu, and imagine them as sources of some kind of data. And for example, you want to observe the data, and you would like to understand which of the two distributions is the one that produced the data that you are observing. Now, if you want to quantify how two general probability distributions, how hard are they to tell apart by this method? So you would like some kind of tool to quantify this hardness or easiness to tell them apart. And these are called information divergences. And so the DPI, which, as Kevin said, stands for Data Processing Inequality, is an inequality that we would like those information divergences to verify. And it basically says that if we take those data produced by the distributions and we process the data in some way, then we cannot make it any easier to distinguish those two distributions. And it looks like this in formulas. So to explain this, I'm going to introduce a few tools, transition kernels in particular, which are already method. We didn't do them, and information divergences. And I'm going to say how we implement some kind of information divergences. And then I'm going to speak about the DPI in particular. So let's start with transition kernels. So first we need some notations. We have X and Y, which are measurable spaces. It means they are sets with some sigma algebras associated, which we call Fx and Fy. And we also say that M of X is a set of measures over X. Now, a transition kernel is a function that takes two arguments. It takes an element of the first space X and a measurable space of the second space Y, and it gives us back a real number, which is non-negative and can possibly be plus infinity. We need two conditions to call this function a kernel. Namely, when we fix the first variable, then we have a measure back. And when we fix the second variable, so if we fix the measurable space, we have a function from X to basically R extended, which is a measurable function. And this is the notation that we use to say that K is a kernel from X to Y. Moreover, if we have an additional condition, in particular that the measures are all normalized and finite, so they are all probability measures, then we call the kernel a Markov kernel. Note that we can actually see this not as a function of two variables, but as a function of just the first variable, X, into the space of measures over Y. And we can encode this second measurability condition as a measurability condition from the space X, the space of measures. And this is actually how it's implemented in Lean. In fact, we have a kernel, which is a structure that has a function from the first space to the measures over the second space, and the condition that this function be measurable. Now, what does it mean for a function to be measurable? Well, we need a measurable structure on the domain and codomain. Of course, we have measurable structures on both alpha and beta here, but we need a measurable structure over the measures over beta. Fortunately, this is already in MATLAB, and there is a natural measurable structure that we can put over the measures, which is this instance here. And it basically says, okay, let's take all the projection maps and let's take the sigma algebra that makes all of these projections measurable, the smallest one in particular. So what are kernels? How do we imagine them? Well, we can see a kernel from x to y as kind of a function from x to y, but not, of course, a usual function, because it takes values in the space of measures over y. But let's just imagine all of the measures to be probability measures, so a Markov kernel. Then we can imagine the kernel as being a stochastic function, which takes an output that's not fixed, but can be different values with different probabilities. And this is a very useful concept because it generalizes two widely used things in measure theory and analysis. In particular, it's a generalization of the concept of measure, of course. In fact, if we take the kernel that always takes the same measure value, it's basically the measure. And if we take a function which is measurable, we can also see this as a kernel. In this way, we just take x and we bring it to the delta. This is the Dirac delta centered over f of x. And that's called a deterministic kernel. It's just like if we collapse all the randomness in the codomain to a single point f of x. We can do various things with kernels. We can combine them. We can combine kernels with measures. In particular, a very useful operation is the composition, which appears also in the definition of the statement of DPI. You see, you can take a kernel and a measure and compose them to obtain another measure. And again, coming back to the analogy with the measure that produces the data, it's like if the kernel is a processing of the data. So it's a transformation of the data, which is possibly random. You can do the same thing with two kernels, actually, which is just like concatenating two different transformations. Another useful operation is the Bayesian inverse, which is some kind of inverse of a kernel. You see it goes from y to x instead than from x to y. And it's very useful in calculations, but it has a problem. In particular, it doesn't always exist. In fact, to guarantee its existence, we need to ask some hypothesis on the spaces, in particular on the space X, and we need to ask that it is a Borel space, so a complete separable metric space with the Borel sigma algebra. These are other useful operations that we can do with kernels, and I just want to say that if you use them in Lean, beware that they have this small m or small k in the symbol. It's an m when the operation is between a kernel and a measure, and it's a k when it is between two kernels. Okay, now we can go to information divergences, which is really an information theory concept. As I said before, an information divergence takes two measures, and it gives you back some quantification of how easy it is to distinguish them. So it gives us back some real number, which can be plus infinity or minus infinity even in some, let's say, edge cases. It doesn't have to be a metric because, for example, it can be asymmetric, but we still want some properties that a good divergence should meet. Now, I'm not going to give you really a formal definition of it, but just some guidelines to make a good divergence. In particular, for probability measures, we should have that the divergence over mu and mu itself is 0. The divergence should be non-negative, and it should meet the DPI. So now I'm going to give a more precise definition of a large class of divergences, which are called f-divergences, where f is a convex function with some additional hypothesis. And you see the f-divergence of mu and nu is this function here. We have two pieces, so an integral part plus some other part. And to understand this notation, let's remind ourselves of what's called the Lebesgue decomposition of a measure with respect to another measure. And that's a way of splitting a measure into parts. It's similar to how we split a vector into parts with respect to another vector. So if we have two vectors, for example, in Rn, you can take the parallel part of the first vector with respect to the second and the orthogonal part. And that's almost the same here. And the first part of the decomposition is called the radon-Nikodym derivative. That's actually a function that's multiplied by the second measure. While the second part, which is called a singular part, is a measure itself. And so this definition can actually be simplified in many cases, in particular when we have that mu is absolutely continuous with respect to nu. This is like if we have two parallel vectors, for example. Then the singular part becomes 0, and so we're left just with this integral part of the function applied to the Rn derivative, integrated with respect to the second measure. These are some examples of notable f-divergences. Probably the most known is the Kullback-Leibler divergence with f of x equal x log x. We also have total variation, chi-squared, Hellinger alpha divergence. And here is the definition that we first gave of f-divergence. So you see, first of all, let's read the second part, so the else branch of this if statement, which is actually not too different from the math definition. In fact, we have this integral plus some other part that, trust me, it corresponds to this other part here in the definition. But why do we need to have an if statement here? Well, it's because of how the Bochner integral behaves. The Bochner integral is the very general version of the integral that we have in MATLAB. But the Bochner integral does not allow infinite values. In particular, you need to give it a function which has outputs in a normed ADCOM group. And it gives you back values in that normed ADCOM group. So we need to give it, for example, in this case, real values, and it cannot give plus infinity because it's not a real value. It gives you back 0 as a junk value. But in the math definition, this integral can actually be plus infinity, and we want it to be plus infinity in some cases. So we just say, okay, if the function inside the integral is not integrable, let's just put the whole f-divergence to plus infinity. Now, this definition actually has a few issues. Let's see them. First of all, we're asking for this function to have R as the domain. But actually, we do not really need negative numbers because the function will only be applied to the radon-Nikodym derivative, which is always negative. But the radon-Nikodym derivative can be plus infinity, so we would like the function to allow infinite values as an input, but right now it doesn't. And that was due to some limitations in MATLAB. In particular, derivatives and convexity work best with real functions, but it's not ideal for our use case. Also, the codomain of R is not ideal. We would like f to be infinity in some cases. That's not really high priority because most actually real examples of divergences do not use plus infinity, but that would still be nice to have. Then there is the Bochner integral, which, as I said, has some issues, but also has other issues that I have not mentioned yet. In particular, it's a bit hard to use it. For example, whenever you have to use very basic properties of the integral, for example, linearity of the integral, you need to provide proofs that the functions inside are actually integrable, because otherwise it gives you junk values and linearity breaks down. And also the output type. Now the output type is the extender reals. That would be fine in general, but maybe we don't really need to allow negative values because we said, for example, that we want divergences to be non-negative. So this is the solution that we are trying to give now, because this is actually not yet in the main branch of the project. This is a refactor that's ongoing. But in this new definition, we solve most of these problems. You see, we use an auxiliary structure, diff function, where we put some hypothesis on the function. And you see that the function now goes from the extended non-negative reals to the extended non-negative reals. So the domain part is fixed, while the codomain part is partly fixed because now we actually allow plus infinity as a value, but we are cutting something because we do not allow negative values for the function. And this, in principle, could seem like a very big problem because, for example, if you remember, the function x log x for the KL divergence needs to take negative values. But actually, we can always rescale the function with a linear part in order to make it non-negative. And the math definition of the f-divergence will not change for probability measures. So it's actually fine. We can overcome this problem. And you see also the integral. We don't have the Bochner integral anymore. There is this minus sign over this integral that we're using. This is called the lower Lebesgue integral. And it's in many ways more limited than the Bochner integral because it only allows, for example, negative values inside. That's why we had to give the ANN real as an output of f. But the good part is that it allows infinite values, both in input and output. And also it's easier to use because we don't have to prove integrability anymore. Okay, so now we're ready to look at the DPI itself. Again, this is the statement of DPI specialized for the f-divergences. Now we should be able to understand what it means. You see, we have the composition with a kernel K, which symbolizes this transformation of data. And so that's a very important result in information theory because it encloses the idea that raw information basically has, raw data basically has the most information. We can never increase information just by processing the data, even if the processing is somehow random. And in the case of distinguishing between two different data producing sources, we cannot make our job easier just by doing some kind of transformation over those data. We actually formalized more than one proofs of this result. I'll tell you why in a bit. And to do those proofs, we also need to formalize a lot of results about kernels, like what is a posterior kernel, a lot of results about hypothesis testing, lemmas about the extended reals, convex function, etc. Now I will just list the 4 different proofs that we gave of it. So the first proof that we tried to give was for deterministic kernels. So it's quite limited because it only applies when the kernel K is deterministic. So if it's a measurable function, basically. And this proof uses the conditional Jensen's inequality, which is still not completely formalized. But as I said, this proof is quite limited. So we would like it to apply also to non-deterministic kernels. Now, to try and generalize this proof, you can do it, but you encounter some problems. In particular, the second proof that you try to formalize, which is a classic proof in the literature, manages to generalize it to kernels, but it needs to compromise on the spaces. In fact, it only applies if the 2 spaces are standard Borel spaces. We use Jensen's inequality. And here we also use the existence of posterior kernels, and that's why we actually need the spaces to be standard Borel spaces. So we try to look for other options that try to generalize it both for non-deterministic kernels and general spaces. And we found a very interesting proof in the literature that uses completely different tools. In particular, it uses the tools of hypothesis testing, which is the framework which I was partly speaking about before, where you have different data producing sources and you have to understand which of them produce the data just by observing those data. And this proof actually defines a new class of divergence, of information divergences, which are called statistical information, which is a very natural thing to define if you are doing hypothesis testing. And those divergences actually satisfy the DPI very naturally. It's a very like 2 lines proof to prove that they actually satisfy it. And then we have a very nice result, which is a representation of general f-divergences in terms of integrals of this statistical information. In this way, we can easily pass the DPI from the statistical information to the f-divergence. Actually, this representation is almost formalized, but we still need a piece, which is a generalization of the integration by parts, because we have integration by parts in MATLAB, but we need a bit more general version of it. So if anyone wants to try and prove it, you're welcome to do it. And so we could stop here. This proof is completely general. But after we did all this work, Rémy actually found another proof in an old paper, which is general as the third proof, and uses techniques which are more standard, so more similar to the first and second proofs. In fact, it uses a very similar proof to the second one, but it manages to bypass the need of using the posterior kernel by applying the first proof. So by applying the result for measurable functions, for deterministic kernels. But was all the effort that we put into proving the third version of the proof completely useless? Well, we think not, because this representation of f-divergences is still nice to have and can be used to prove other things. So I'm going to show you that if we have, yes, we have, I guess, a few more minutes. So I'm going to talk about this quickly. Let's imagine that you have, as I said before, 2 probability measures, and you try to distinguish between them, and you have a prior pi, which is your prior probability, so the probability you attribute to mu being the true distribution or nu being the true distribution. This I, which is the statistical information, measures the difference in performance between the best possible estimator, which is a function that tries to understand whether it was mu or nu to produce the data. So this statistical information measures the difference in performance between this ideal estimator and a blind estimator, which is an estimator that cannot see the data. So it just has to guess basically randomly. And so this is, in this sense, it is an indicator of how hard it is to distinguish them. Now, the nice result that I was talking about is this integral representation of f-divergences, which says basically that if you have some function f which satisfies the hypothesis that I talked about before, and a little bit more. Now, here I'm also asking for this f prime plus, which is the right derivative of the function 1 to be 0. This is needed just to have this nice form of the representation, but we have another a bit longer integral representation which doesn't need this hypothesis. And this is the same with the hypothesis of mu being absolutely continuous. And so you see we have this integral of the statistical information with respect to a measure which is called gamma f, which is the curvature measure of f. It's basically just a measure that depends on the second derivative of f, in the case that f is 2 times differentiable. Okay, so I'm going to wrap up and just say what we did, summarize what we did during the project, which, as I said, is still going on partly. So we added the definition and a lot of API for f-divergences, as well as some concrete examples of divergences. We added the hypothesis testing framework, definitions for it, a few lemmas, and also the connections with f-divergences. Of course, the DPI for f-divergences, and also other results, like results about posterior kernels, results like about other operations on kernels, and about e-reals, convex functions, etc., that were needed for the project. And what we still need to do, well, as I mentioned before, we have two results that are in the project but are not proven, which are integration by parts, the generalized version, which could be probably proven using Riemann-Stieltjes integrals, which, as far as I know, are not in MATLAB. Also, we would need the conditional genesis inequality. This should be quite a small project, actually. And we need to complete the refactor of f-divergences. We have definition now. We need to adapt all the lemmas. And we need to port those results to MATLAB. So other people mentioned how important it is to get definitions right, how important definitions are. And I think one lesson learned here is that yes, definitions are definitely a crucial part. In our case, we understood that we had to change the definition quite later on. So the time it is taking to do the refactor is quite big, but I think any time is good. Is a good time to change definition, because if we waited longer, we would take even more time to do it, and eventually I think we would need to do it because it wasn't, the old definition was not really fitting to the mathematical one. So thank you very much for your attention, and if you have any questions, I'm here to take them.